I'm going to go ahead and start finishing up the review of Unit 1, which sort of sets the stage for the remaining units. So I'm going to hit periodic trends, valence electrons, and review a little bit of this beginning material. When you look at Schrodinger's equation, and if you're thinking about atomic structure, what we're looking at are these mathematical equations that are quite complex that describe an area in space carved out where your electrons would reside in orbitals. Being a mathematical probability, again, it is a math equation that gives us the probability of finding an electron. There are 4 quantum numbers that help describe the location of the electron in the orbital. You have the principal energy level, or the N quantum number. This would be, if that's your nucleus, you've got energy level 1, 2, 3. These are the distance and energy of the electron. You then, within those energy levels, have your sublevels, which are your shapes, S, P, D, and F. Your shapes can have orientations based on how complex that shape is. So if you're talking about the P sublevel as a dumbbell, then the three-dimensional space that can occupy has 3 orientations around the X, Y, and Z axes, and all overlapping would give you that sublevel. So the orbitals make up the sublevels, and in each orbital you can have a maximum of 2 electrons with opposite spins. So if you're looking at your S orbital, it's a sphere. So if you were imagining your nucleus, it's somewhere inside here, and this 3-dimensional shape is the S orbital at the first energy level. If you move to the second energy level, you have another S orbital. The S will always fill first in any energy level because it is the simplest space that 2 electrons can occupy. At that second energy level, however, it is larger and you can have the P sublevel. The P sublevel has 3 orientations. So it's got 3 orbitals around the X, Y, and Z axis. They all overlap, giving you the P sublevel. So the P sublevel can have a total of 6 electrons because there are 2 electrons in each of the orbitals. The P orbitals have 2 electrons each for a total of 6 in that sublevel. When you move to the third energy level, this is the first time that the D orbitals show up, and there are 5 D orbitals. There's a basic cloverleaf shape that can orient itself in 5 different directions. I'll go back through that a little slower. So 5 different orientations of that mathematical shape gives you the total D sublevel. And then your F orbitals, there are 7 of those for a total of 14 electrons. So remember, all you're looking at when you look at this shape, and you're never going to have to pick this shape out of a lineup, you just need to know that there are 7 orbitals in the F sublevel. So if we're looking at a quick review of that, that gives you at the first energy level, you have 1 sublevel, the S, which has 1 orbital. The second energy level has 2 sublevels, S and P. The third has SPD, and the fourth has SPD and F. So each energy level, the fourth energy level has 4 sublevels. The second has 2. Very convenient way to remember. The sublevels are located in your energy levels, and then in your sublevels you have a particular shape. And again, your S, your P, your D shape. None of these are necessary that you know them, not at this level of chemistry. What is necessary is that you recognize how many orbitals are in each sublevel. And of course, it's 1, 3, 5, and 7, something you've seen from last year chemistry and this year's review. So make sure that you know, and you can look at the periodic table and count out by now the SPDF blocks and so on. So when you write an electron configuration, you are writing the number, tells you the energy level. Okay? The sublevel is written next, and the number of electrons as a superscript. When you're filling your orbitals, we already know that there's going to be a jump when you finish filling the 3p rather than fill the 3d. You're going to go ahead and fill that 4s. And we looked at electron configurations many times in first-year chemistry and second-year chemistry. You want to be able to relate those electron configurations to the PES diagrams that we talked about last time. There's your first energy level with its 2 electrons. Further from the nucleus is your second. Further away and held less tightly, higher in potential energy, but lower in binding energy. So further from the nucleus, remember, there's your peak. That means that your binding energy, you're held to the nucleus less tightly, but you do have greater potential energy. The further you are away from the nucleus, so wherever those energy levels are located, the further you are away, the greater the potential energy. Make sure you get potential energy and binding energy straight. So then you would move, there's your 3s right there, and then your 3p, and this element has 3p1. The reason that they fill in this order is basically because of electron repulsions and complexity when you have that many electrons and that many orbitals. So the 4s is of lower energy. Okay? So if you stop and look, if we went back and looked, let's go back, our 4s, well, we didn't get up to the 4s in this one. Our 4s would have lower energy. Okay, so there's your lower potential energy, even though it is further from the nucleus. So we do believe this occurs based on electron-electron repulsions and complexity. You really need to know nothing more than the 4s fills before the 3d, something you already know. Your valence electrons are always your S and P electrons in the outermost energy level. They are never the D. Okay? The D is not going to fill until after the S. The P will fill after the D in that same quantum number, but the D electrons are always one energy level behind the S and P. So they're never the outermost electrons. The valence are the outermost electrons with the highest principal quantum number. An orbital diagram simply helps you to see where those electrons are paired and unpaired so that you can figure out bonding and non-bonding electrons later on. So when you're following your electron configuration rules, remember, you have to fill lowest energy levels first, then at the most put 2 electrons in any one orbital with opposite spins, and then when you're filling equal energy levels like a P or a D, you will fill those orbitals up separately with parallel spins before you will go back and fill them up with pairs and opposite spins. So Aufbau, Pauli, and Hun rules always have to be obeyed. The shorthand method for writing electron configurations is, of course, using the noble gas and then whatever energy levels follow that. You have a periodic table. The periodic table will absolutely guide you through. Let's just look quickly. If we were going to do bromine, we really don't want to write 1s2, 2s2, 2p6, and so on. We can look at the previous noble gas, argon, and write argon in brackets. And then once we've done that, we can then add the remaining electrons to get to bromine. So that would be the 4s2, 3d10, and 4p5. Now, pay attention on the exam. They often will say the complete electron configuration. And if they want the complete, you're going to have to write out 1s2, 2s2, 2p. So if they don't say anything, you're free to write the shorthand. But if they say complete and you write the shorthand, no credit. So as we move from this basic electronic structure of the atom, we're looking at where these electrons are going to be able to give us bonding. Right now, we're simply looking at the fact that we know that the noble gases have a very stable electron configuration. They all have 8 electrons in their outer orbitals. Of course, helium has only 2 because it's so small, but all of the other elements are going to try and acquire this noble gas arrangement when they bond. Now, we're not at bonding yet, but we are looking at where those electrons are located. So we're looking to fill up our s and p orbitals by undergoing those chemical reactions to gain a noble gas configuration. So every element in group 1 has ns1, meaning n, any of the quantum numbers, 2 through 7, ns1, 1 valence electron. Moving over to group 2, we have 2 valence electrons. We're going to skip the transition metals because they do not contain valence electrons. If we jump all the way over those Ds into group 13, even though if we were in this area right in here, in order, after we fill 4s1, we know we're going to fill 3d and pop back out at 4p, but they are not the valence electrons. So even though you will have s and you will write and fill those Ds and then come back and fill the Ps, your valence electrons will always be just the S and P. So everything in group 13 has 3 valence electrons. This comes in handy later when you're doing your Lewis dots and having to figure out how many valence electrons are available to bond. Group 14 has 4, group 15 has 5, then of course 6 in oxygen's group. Your halogens all have 7, and back to your noble gases with S2P6. If you are asked to write an orbital diagram on the AP exam, I don't think you'd have to write anything this long. They might stop it right in here, but they would be looking for you to know that you do not pair up until you need to, and when you do, you have opposite spins. Periodic trends then follow right after learning where those electrons are located. So you've got first your atomic radius, and really this controls all of your other trends. The atomic radius is usually measured as half the distance between the 2 nuclei of an atom, but you're simply looking at the size of that atom. And I did not understand why the gentleman that gave the presentation did not talk about Coulomb's law, because it's a big deal. It's a big, big deal. And you need to use it for all of your periodic trends and discussion of all kinds of bonding. So now we're looking at the attraction of the nucleus and the electrons wherever they are located. And let's assume this is the outer energy level. So opposite charges attract, we know that. If you have a greater number of charges, then you're going to have a greater attractive force and you're going to be held stronger. Right now, you're looking at that number of protons increasing and pulling those outer electrons closer, which is always your argument for ionization energy and radius. So when you are getting a shorter distance between, so here you've got a greater charge pulling you together. If your distance between your 2 charged particles is much closer together, then your force of attraction is much greater. So again, this controls all of your trends going down the periodic table and across the periodic table. So when we look at these questions, we're looking at discussing them with Coulomb's law. Coulomb's law says the energy, or the force of attraction, is equal to the charges, opposite charges, over the distance between those two charges. So Coulomb's law, charge over distance. You're really looking at the difference in those charges. You can use uppercase or lowercase q. No one really cares. So the attraction experienced by the negatively charged electrons to the positively charged nucleus is Coulombic in nature. So you've got to use Coulomb's law and this equation when you are trying to discuss the relationship. So the equation is very simple, okay? The energy required to separate the electron, or how tightly that electron Q1 is from the nucleus, is directly proportional to the charge on the nucleus and inversely proportional to the distance that separates the electron from the nucleus. So the greater the nuclear charge, the greater the attractive force. The closer the distance, the greater the attractive force. The further the distance, the less the attractive force. So when you're going down the periodic table, we all know you get more electrons, which gives you more energy levels. They fill up. Obviously, the atom gets larger. But your real discussion in that has to be based on the distance of the nucleus from that outer electron. So don't just say that, oh, well, they gain more energy levels and so they get bigger. You want to talk about the fact that that outer electron, wherever it's located, is further from the attractive force of that nucleus. Therefore, there is less energy to remove that electron. Or the radius is larger because there's less of an attractive force and that electron cloud can expand away from the nuclear pull. As you move across the periodic table, atoms get smaller. Again, in the beginning, that's a trend that can be difficult to understand, but if you're looking at Coulomb's law, as you move across, you are adding electrons to the same energy level. Your outer electrons are added. Remember, it's only outer electrons that we're looking at that control this radius. You're looking at your S and P electrons, and as you move across, they are added to the same energy level. 2s and then the 2p. Or if you were at the 3s, you'd fill 3s2 and then 3p6. 4s2, 3d10, but 4p6. So you would be filling the same energy level with those outer electrons. But as you move across, you get tremendous greater pull because you have more protons in your nucleus. So it's the increase of those protons that pull the electrons that are no further away closer to you. So in Coulomb's law, that's this part of the equation, the charge difference, the increase in that nuclear charge. So radius trends, okay? You never want to discuss a free response with, oh, the periodic trends say it gets smaller this way and bigger that way. That is not an explanation. You need Coulomb's law. So I'm assigning you some FRQs so that you can learn to word those correctly. So ionization energy is based on radius. How close is that electron to the nucleus? How tight is that pull? So if you have a small radius of your atom, then your electron is held tighter. It is more difficult to remove it. The larger the radius, the easier it is because you do not have an attractive force holding that electron. Isoelectronic species are interesting, and you certainly could get a question. You simply need to recognize that you're looking at a series of ions that have the same number of electrons, hence isoelectronic, but they have different numbers of protons. So the fluoride ion, the oxide ion, the nitride ion all have the same. If you're going to lose 3 electrons, lose 2, lose 1, you have 10 electrons in all of these species. Same here as, you're going to be gaining those electrons. -3, -2, -1, my mistake. Gaining them to get 10 electrons. Here you're losing those electrons to get your 10 electrons. Isoelectronic, but with different numbers of protons. So your more highly charged positive ion is going to have a larger number of protons to electrons. So its radius is going to be much smaller than your more highly charged negative ion. Any successive ionization energy. So if you take an electron off, you now have a greater positive charge to negative, so you removed your electrons from a neutral atom. You now have a greater positive pull, so your radius is going to get smaller. It's going to be more difficult to remove the second electron and more difficult to remove the third. This is because each time you remove an electron, you have a greater nuclear pull compared with the number of electrons in your atom. So each ionization energy always increases from the previous. So here's a question from a free response, and it says that magnesium and fluoride ions are isoelectronic, and they are, and you know that because the fluoride ion would gain an electron. Fluorine is not isoelectronic, but the fluoride ion certainly is. So it's ions that are isoelectronic. Magnesium 2 plus has 10, fluoride -1 has 10. So which ion has the smallest radius, and explain. So I'm not going to read through all of these in detail because I want you to make sure that before you do your FRQ, you study through some of these so you can pause the video and read these answers and make sure you understand them so that you can express your answers back to me on your free response. But it's based on the same electron configuration, same number of electrons. Look at the protons. Magnesium has 12, fluorine has 9. Go ahead and make sure you add up all the protons, electrons, get it straight in your head. So if you have more protons, then you're going to have a greater force of attraction based on Coulomb's law. You've got a greater nuclear charge. Therefore, you will increase your number of protons and decrease your radius. So if you're looking at a trend like this, so we just said ionization energy increases every time you remove an electron because the number of protons in the nucleus is greater. So it makes sense ionization energy 1 and 2 and 3 increased, but then all of a sudden ionization energy 4 is huge in comparison. So what you want to recognize when you're looking at this would give you Al plus 1, this would give you Al plus 2, and this would be Al plus 3. This would be Al with a plus 4 charge. If you are getting a plus 4 charge, you now have gone down into the core electrons. So you're one energy below that. You're in the core electrons, and it takes a tremendous amount of energy because you're so much closer to the nucleus, and now you're not a valence electron, you're a core electron. This gives you, so the ionization energy before the big jump will tell you where the most stable arrangement for that ion is. Same thing here. We know magnesium has a stable plus 2 ion. Look at the amount of energy to form a plus 3 ion. So again, you can tell that these first two ionization energies would give you the most positive, most stable positive ion with a plus 2 charge. So why is the first ionization energy for lithium less than that of neon? So anytime you are given a periodic trend question, look at your periodic table. Here's lithium, okay? We're looking at neon. So lithium and neon are in the same row. We know that if you're moving across the periodic table, that radius decreases. It's fine to say that in your head. You really cannot just say radius decreases. You must say electrons are being added to the same energy level, but you have a greater number of protons, so a greater nuclear charge, which causes your radius to be smaller. They may draw drawings that show you that it may look like the radius is the same, but you know And they're trying to trick you with all these electrons. So maybe you're thinking, oh, I'm not sure about that. Has nothing to do with those electrons are all being added in the same energy level. I don't care how many of them there are. It's that increase in that nucleus that is giving you that greater energy. The radius is smaller because the protons and the nuclear charge is greater, so the electron is held tighter, so the ionization energy is greater because it's harder to remove that electron. These are the steps that they're going to want to give you that credit. These are usually some of the lowest scoring questions on an FRQ because students don't state the answer correctly. Another one, you've got two shell models of two neutral atoms. They're not drawn to scale. Which has the smaller radius? Well, they tell you they're neutral. So this one has far more electrons. So that means you're moving across the periodic table. That again is your Coulomb's law of increased nuclear charge. So that is going to give you the smaller radius right here. Which species has a smaller radius, the calcium or the calcium 2+ ion? Well, if you're looking at the calcium 2+ ion, they both have the same number of protons, but the calcium 2+ ion has lost 2 electrons, which gives you a greater proton to electron ratio. You might even want to pay attention to the fact that you've got electrons in different energy levels. So if you're closer to the nucleus, so your calcium 2+ has electrons in the 3rd energy level, while calcium neutral has electrons in the 4th energy level. So you're looking at a shorter distance and a smaller radius, okay, because of those numbers of protons. And here again is another comparing ion. The fluoride ion, however, is going to have a larger radius than the neutral atom because now it has gained electrons. So to be the fluoride ion, it has gained electrons, 1 extra electron. So now it has the same number of protons, but greater electrons in the fluoride ion. The fluorine atom has a smaller radius. The fluoride ion has a larger radius. So one of the things you want to look at as a general rule, cations, positively charged metal ions, are always smaller than the parent atom because they have more protons to electrons. And anions are always larger than their parent atom because they have more electrons to protons. This is an ionization energy. So if you're looking at ionization energy of magnesium and calcium, the first thing you want to look at is, well, I know that the radius of calcium is larger than magnesium, so magnesium is smaller. You also have energy level 4 and 3, the difference between them. So read through this answer, make sure that you understand in the end, you have to talk about energy. If they're asking you about ionization energy, you need to make sure you're clear that it takes more or less energy to remove that electron. And your Coulomb's law argument will support that. Same thing with this question. Again, on your own, read through. So you're looking at ionization energy. First, look at radius, because you know that the smaller the radii, the closer that electron is to the nucleus. Once you come up with what you're sure is true, then write it using the correct wording. Sodium has a larger radius. They have valence electrons in the same shell. The valence electrons in chlorine experience a greater nuclear charge. Anytime you are going this way, this direction, you're looking at nuclear charge. Anytime you're going down the periodic table, you're looking at the distance or the radius of those atoms. Distance and radius, same idea. And here you're looking at the second ionization energy. So this is a pretty complicated question unless you break it down. So they tell you that the second ionization energy of sodium is much greater than magnesium. So if you look at where sodium and magnesium are located, you can tell that your magnesium is a smaller radius, but you also are looking at removing those electrons from different energy levels. So the second electron, so they're looking at the second one. So when you remove the first electron from sodium, okay, you drop down to a lower energy level. So to remove the second electron, you're now at the second energy level where magnesium is further away. So this is a little tricky question here that you want to read through and make sure you understand. Again, two shell models, not drawn to scale. Which one would have the highest ionization energy? If you get a particle diagram, look, you're filling only two energy levels here and 1, 2, 3 here. So clearly this element is larger. That means that it's going to be easier to remove the electron because it is not held as tightly, again, based on that distance. So you had to be moving down the periodic table in order to add those energy levels. That's always distance. Electron affinity is a new trend that's been added this year. I don't know if you'll see it because of the limited exam, but electron affinity is just the desire that an atom has to gain an electron. So we know that halogens are able to gain electrons and fill up their orbitals due to their electronegativity and lots of things. We're actually, electronegativity and electron affinity are pretty much the same. Electronegativity is the desire for that electron in a compound, while electron affinity is the desire for the electron just in an atom. So the smaller your atom is, the easier it is to hold on to extra electrons. So there's a short video that I'll play for you.
Electron affinity is the energy change that occurs when an electron is added to a gaseous atom or ion. For example, when an electron is added to a neutral gaseous chlorine atom, 349 kilojoules per mole is released. In the case of chlorine and the other halogen elements, addition of an electron to the neutral atom is an exothermic process. Addition of an electron.
So when you're looking at electron affinity, they will often ask you about the negative electron affinity and which one is more negative. So you're looking at energy released as you add an electron to an atom. And they're probably going to focus on the halogens, which are the easiest elements to add an electron to. And if you were looking at the size, fluorine being smaller has a greater electron affinity because the nucleus can hold on to that electron versus a larger halogen where the nucleus is further away. So you would probably have a more negative electron affinity, meaning more exothermic, releasing more energy with a smaller halogen. So your ionization energy and your electron affinity all increased as your atomic radius decreases going across the periodic table. Remember, it's that radius that you focus on when you're going down the periodic table, and it's that nuclear charge that you focus on when you're going across. So once you've got an idea of what those periodic trends are, why things want to gain electrons, give them up, radius, attraction for electron, then you're ready to move into bonding. And you're looking at the two extreme forms, and I'm going to go through this quickly because it probably is the beginning of our next unit. Even though it's mentioned here, you have ionic bonds, covalent bonds, transferring electrons, sharing them unequally, sharing them equally. You've got mixed type of bonding. We would all call sodium sulfate an ionic compound, but the entire sulfate ion is covalently bonded. So chemists make a determination of an ionic compound as containing a metal ion. And as long as it has 50% character, it's ionic. And that 50% character draws the line right at metal, non-metal. You can see that you can have covalent compounds that have a high amount of ionic character and ionic compounds that have low ionic character. But That is based on your electronegativity and that whether you're sharing or transferring electrons. So a transfer of electrons may or may not be complete, but you're looking at metals, and nonmetals are going to undergo this type of bonding. So if you have a low ionization energy, like metals have large radii, their electrons are not held tightly, and a high electron affinity, we just said your nonmetal elements are smaller and more able to hold on to electrons, you're probably going to get an ionic bond. So metals, nonmetals, first year chemistry stuff. The forming of that bond is an opposite charge attraction, electrostatic attraction, as that electron is transferred from the cation to the anion, forming charged particles that are then pulled together and held tightly. So if there's your electron configuration and you bring sodium, metal, and chlorine in contact with each other, you're going to transfer that electron to get your noble gas arrangement and form that stable NaCl 1:1 formula. The properties of ionic compounds are all based on that electrostatic attraction. They have high melting points, they're brittle, they don't conduct electricity because their ions are not free to move. You're able to differentiate the energy of an ionic compound also based on Coulomb's law. So when we first looked at Coulomb's law, it's attraction of the nucleus for the electron, which gives us ionization energy and radius. Now we're looking at ionic compounds, and we have charged particles. So now we're looking at the opposite charges, cation and anion, attractive charges, and the radius or distance between those charged particles. So Coulomb's law will give us an idea of how strongly we are bonded. So radius or distance is fine to put at the bottom when you're thinking about that energy or force of attraction. So that force of attraction is called lattice energy. It's the change in energy when your separated gaseous ions come together to form that stable ionic compound. And it is quite exothermic. It's the driving force for that reaction to occur. When we get into thermodynamics, we talk more about that lattice energy. So the larger the ions are, the larger the ion charges are and the smaller the radius, then the stronger that bond energy or the larger that bond energy will be. So when we say that large bond energy, we're looking at lattice energy, and we want it to be the most exothermic. So if we're looking at lithium and cesium fluoride, we'd have equal charges, +1, -1 for each ion. So your Q's values would be the same, but your distance between those ion centers, your lithium is much smaller than your cesium. So the reason you have this larger energy is because your radius is so much smaller. So smaller radius gives you a greater attractive force. If we move down to the next one, sodium bromide and sodium iodide equal charges. So if the charges are equal, we're looking at radii. Sodium is the same, but your iodine is a much larger ion. Therefore, your nuclear centers cannot get as close to each other, so your lattice energy is not as strong in sodium iodide as it is in sodium bromide. When sodium bromide forms, it releases much more energy and forms a much stronger bond than sodium iodide. Barium chloride and barium oxide. So when you're looking here, now you're looking at charges. This is a +2, -2. This is a +2, -1. You're not looking at how many of them there are, just what is that charge. So now you're looking, anytime your charges are greater, that is going to control your lattice energy. So your barium oxide is a much more exothermic lattice energy. Again, look at these carefully. Make your decision. You've got sodium sulfate with a +1, -2, and calcium sulfate with a +2, -2. So there's no reason to look at the distance between your centers. Your greater charges, these would be the product of those charges. So +2, -2 is a 4 charge, where over here you're going to have a 2. So you've got twice the attractive charge force in that calcium sulfate. Potassium fluoride and potassium oxide have to be based on charges, not on radius, because you have a higher charge in your potassium oxide. So your potassium is held stronger to the oxide ion in that lattice. Think about what you think is controlling these before I click the answers. Lithium oxide and sodium sulfide. Just because the formulas look the same, that's your first mistake. So you've got a +1, -2, and you've got a +1, -2. So your charges look pretty good. So then you must be looking at radius, and you've got lithium and sodium. So lithium is smaller than sodium, and then you're also looking at your sulfur and your oxygen. So these nicely work out to give you the lithium oxide with the greater lattice energy. And here your magnesium oxide, based again on the charges are the same here, but it is that radius that controls that. So be able to pick out based on charge or radius. They're not likely to confuse you by going diagonally and have a higher radius in your cation and a lower in your anion. They're just not going to do that. You just basically need to understand Coulomb's law and attractive forces in ions. Your electronegativity then is going to explain, or I guess it does explain, why you have an ionic versus a covalent bond. You're looking at the ability of an atom to attract electrons to itself based on pretty much its radius. Okay? So the tendency for an atom to attract electrons when it's chemically bonded, it's going to measure whether or not we're going to transfer electrons or share them equally or unequally. And it's really nice to know that fluorine is the most electronegative element on the periodic table, and then you can base electronegativity on everything else compared to that fluorine. So if you have a large difference in your electronegativity, you're probably ionic. If you have very little or no difference, you're a nonpolar bond. And then intermediate distances would be polar, but not quite ionic yet. So large differences, no one is going to ask you to have any numbers. We've already said. You know if it's a metal or non-metal, it's ionic. You can compare the strength of the bond using Coulomb's law. And if it's covalent, you also use Coulomb's law when we get into that. You're looking at the radius of that atom and how close it is to the nuclear center of another. But just remember, fluorine is the most electronegative element. So when you're looking at electronegativity and how strongly you're going to have that character, always look to fluorine to be the most electronegative. So it says sulfur is more electronegative than calcium. Explain why this is and justify claims using your knowledge. So you're probably tempted to say, well, it's the most electronegative element is fluorine, and chlorine is closer to fluorine over here, but you've got to give more than that. Electronegativity increases as radius decreases. That is why fluorine is the most electronegative. When two atoms are involved in a chemical bond, the valence electrons experience a greater attraction to the positive nucleus that's closest to them. So the smaller your atom, they're going to hold on to those. According to Coulomb's law, the force of attraction increases as the distance. So if you look at where your sulfur is located, it's up and to the right of calcium. Therefore, its radius is much smaller. That lends you to that greater attractive force and the ability to hold those electrons. So the difference in electronegativity is going to determine the types of bonds, and that moves us into our next chapter on types of bonds.